What's up, y'all? We are in section 3.2 now. Section 3.2, this is pre-calculus. This is a video. This is a piece of paper. This is a pen, yada, yada, yada. Section 3.2, exponential and logistic models. We'll just call it exponential models. They kind of all fall into the same camp. So section 3.2, exponential modeling. Okay, and mathematical models are when we take a math equation and we make it equal something real. When it's actually modeling something real. Let me zoom in a little bit. There we go, almost there, and great. That's a little better. Okay, so exponential modeling. Let's do annual percent change. Annual percent change, and it's we usually I'm going to use the function p here in terms of a population. So function p of t, time is changing over time, things will change. P sub 0 or p naught, N-A-U-G-H-T, it's not N-O-T. It's that old English word that means 0, p naught. So that's the initial population. Of 1 plus r is the rate in the rate as a percent, as a decimal, to the t power. Okay, so an example of this would be p of t equals 400. 400. So the initial population was 400. Population doesn't just mean people. It can mean bacteria. It can mean wild geese. It can mean anything. Okay, so this is 0.972 to the t power. So this is 1 plus the rate, is this right here. And I can solve for the rate. I can solve for the rate. Let's see. 1 plus r equals 0.972. So what is the rate? We'll subtract 1 on both sides. And I'm not going to think right now. Let me just do it. 0.972 minus 1. Should be able to do that in my head. R equals 0.028, and it was negative. It was negative. So this number here is between 0 and 1, so the value will be going down. The percent change will be negative. It's decreasing. You could also say this is negative 2.8%. So to find the percent, you need to subtract 1 from whatever number is there, or the percent change. Now, you could probably just look at that and say, well, how far is this from 1? And just do the math in your head. Especially if it's just like 0.97, it would be 3% decrease. So sometimes the math is a little bit easier to do. So that's annual percent change, or whatever. If it says change per minute, then put that in for the time. It doesn't necessarily have to be yearly, but that's what we usually use it for. So let's see. Let's do something a little different. We're going to model bacteria growth. We're going to model bacteria growth. We're going to say it doubles every 47 minutes. This population of bacteria doubles every 47 minutes. It doubles every 47 minutes. Okay, and this is depending on the problem. They can tell you it doubles at any interval. Just make sure you hang on to that word minutes there. Okay? And here's the problem. If you start at 100, how long does it take to get to 1,000,000? If you start with 100, how long will it take to get to 1,000,000? If you start with 100, how long will it take to get to 1,000,000? There we go. Question mark. This population is going to look a little different. This model is going to look a little different. Let's say P of t equals 100. Still start with the initial value there. It doubles, so I'm going to put a 2 here for my base. And this kind of makes sense. This is the rate plus 1, right? Because the rate is 1. The rate is 100%. You're going to add 100% onto the other. So the rate was 100%. Add 1, you get 2. The power is what's going to be a little bit different. I have to do t over 47. And I could do a little bit of work to find what this value actually is without the over 47 there, but it's easier just to do it like this. Okay, so it doubles every 47 minutes. It doubles every 47 minutes. And another way to think about this is that if you put 47 in here, well, those will just cancel out. 47 over 47, leaving you with 100 times 2. So they would double after 47 minutes, because that would just go away. Okay, I want to know how long will it take before you get to 1,000,000. So let's say 1,000,000 equals 100 times 2 to the t over 47. I have a new trick for you today. I think it's new, I'm not sure. But to use that trick, first we have to make this equal 0. So let's cross that out and do minus 1,000,000 over there, and that's 0 equals that. Get out your calculator, and under math, whoops, that's out of focus now. And under math, go to solver. Okay, so let's go ahead and hit math, because it's 0 equals something. This will actually solve it for us. Whoops, math. At the very bottom is solver. Math 0 is something called solver. So go ahead and select that. And I already have this in from the other day. Okay, let me go push up to edit the equation. So I have 100 times 2 to the x over 47 power minus 1,000,000. Minus 1,000,000. Let me fix this here. I wrote it wrong. There we go. Okay, and then if you push down, and let me get rid of that because that was the answer. Above the enter key, you see solve in green. Above the enter key, you see solve in green. You probably can't see it in this video because of the resolution, but it's right there. So hit the green button and then solve. Hit the, and I think I might need an initial value. I'm not sure. No, I don't. Hit the green button and hit solve, and that will tell you what x needs to be. So that's kind of cool. It's just numerical, but it will, find the right answer to 15 or to how many digits. So that's cool. So our answer is 624.5 minutes. $624.5 minutes. And we can put that in hours as well, but remember it was minutes to start with, so I have to use minutes here. I could also put that in hours, so remember the calculator will remember what x is, so if I quit and then just type x again, it's still that value until I do something else in another window. So I could take that divided by 60, just to give me an idea, it would be 10.4 hours. Just to understand my answer a little bit better, I'll say 10.4 hours. Okay, one last thing I want to throw in here is a logistic. We didn't really talk about it that much. How does the function actually relate to the numbers in it? Okay, so let's say f of x equals c over 1 plus a times b to the x power. Okay, well, let's see. This is logistic function has a horizontal asymptote, and it's going to be at 0 with this model, and another horizontal asymptote up there. Okay, this asymptote here is y equals c. Whatever the value of c is there, that's where that asymptote will be. You also have the y-intercept here. Okay, if you plug 0 into this equation to get the y-intercept, that's going to make b to the 0 power. That's going to make that 1. Anything to the 0 power is 1, so that will go away. So the y-intercept is 0 c over 1 plus a. So if you're given a problem with a couple points, you need to find this equation. Start with c, put the value of c in, and then you can solve for a using the y-intercept, and then you can solve for b using another point. A couple of these will only give you a couple points, so you can't use the regression option. they kind of take that off the table for you. So, so those are your notes for section 3.2.